Okay. Okay. So it's our great pleasure today to host Professor Arijit Khan from Aalborg University in Denmark. So Arijit got his PhD from the University of California at Santa Barbara, and he then worked at ETH Zurich and the Nanyang Technological University in Singapore. He's a very prolific researcher. He's an NRTP senior member and an ACM distinguished speaker. And he's gonna talk to us today about his work on graph on machine learning, and in particular applied to graph neural networks. Arijit, the floor is yours.
Thanks, Themis, for the very kind and nice introduction. So, hi, good afternoon, and welcome to my presentation, Synergy of Graph Data Management and Graph Machine Learning. My name is Arijit Khan, and I'm an associate professor at Aalborg University in Denmark. It's my great pleasure to be here, and thanks for having me. So, some background about myself. I did my PhD from UC Santa Barbara, and then I was in ETH Zurich as a postdoc. I had been an assistant professor at Nanyang Technological University in Singapore, and for the last couple of years, I'm in Aalborg University in Denmark. So let's start. Okay, graph data can be found in almost everywhere, and we can categorize them into two general classes. In one scenario, we see many small graphs, and they can be stored in a graph database. Examples could be a number of chemical compounds. Each of these chemical compounds can be modeled as a graph with the atoms as nodes and their bonds or connections as the edges. And we have many such chemical compounds, so they can be stored in a graph database. Similarly, we can think of human brains. Due to fMRI, we can get the graph structure data out of the human brains, and then there are many such human brains that we can take fMRIs and we can store them in a graph database. And then on the other hand, we also see one very large scale graph data, such as the social networks, the knowledge bases, the transportation network. And these days also in machine learning, we see a lot of recommendation type of data, such as movie recommendation, item recommendation, etc. And they also have a very large scale graph structure data with them. These graphs also come in many different varieties or formats, starting with static graphs that do not change a lot over time, such as chemical compounds. And then on the other spectrum, we see dynamic or time evolving graphs. So think of the traffic network of a city over a period of time, and we can get this kind of historic or temporal snapshot graphs. And then in the social communication data, the graph data or the graph edges come as very fast, rapid streams. We can also have uncertainty with the graph data. If we think sensor network, then the connections or the links between two sensors, they fail with certain probability. And that means we can associate a probability or uncertainty with the edges in the graph. We can have heterogeneous graphs where the nodes or the edges can be of many different types, such as in the diiP network, we have different authors, their publications, conferences, journals, venues, years, etc. So we can have nodes of many different types and also connections or edges of many different varieties. Knowledge graph, which is very popular these days, and I will speak about them. It's also a type of heterogeneous networks where we can have different types of entities and there are different types of connections. And that's not all. These days, researchers are also looking at more complex, higher order interactions, such as hypergraphs or simplical complexes. Examples could be the publications in diiP. In each publication, usually it is not just one or two authors, but a set of authors together, they write a paper. So that means it's not the pairwise connection, but it's a connection covering multiple entities, and that's why we can create hyper edges. So clearly, these are so many varieties of graph structured data, and that's why the downstream applications are also very different. With the popularity of machine learning, graph machine learning or graph deep learning is a very hot topic. Now, these deep learning techniques or machine learnings, usually they work on very regular or grid structured data, but graph can have irregular shape. So that's why one can convert the graph in the form of vector representation. For example, one can create the vector representation of the nodes, of the edges, or of the graph itself. And then we can apply different machine learning models for various downstream tasks over this vector representation of the graph data. The downstream tasks would be graph classification, node classification, entity resolution, link prediction, etc. Of course, this learning can be end-to-end because of the deep learning techniques. That means we do not need to generate these kind of embeddings explicitly, but the deep learning models can take care of such embeddings in them. And one popular graph deep learning model is graph convolutional neural network, which follows the popular message passing paradigm. The key idea is each node have its own feature, and then over time, the nodes, they propagate their features in the form of messages to its neighbors. So that means the neighbors get the feature of its neighboring nodes. And then if you do it for multiple rounds, that means you can get the information from your neighborhood, which is beyond one hop. And this neighborhood information are aggregated and we get a representative, a new representation for the nodes, and that can be used as the vector data corresponding to each node. And then you can train your machine learning model. So that's the key idea of the graph neural network or graph convolutional neural network. And then these graph machine learning models are used for different kind of downstream applications, such as node classification. So think of a financial transaction network such as blockchain. And in this blockchain, we want to classify if an address or an account is malicious or not. So that's a problem of node classification. Or we can do the entire graph classification. Given different kind of chemical compounds, we can classify them into different classes, such as mutagenetic or non-mutagenetic. Or if this chemical compound is going to have some kind of side effects, right? And then link prediction, right? That could be another downstream application where we see that in social networks, we often get recommendation that you should get connected to another user, etc. And that's basically predicting a link. And this could also be useful in recommendations such as item recommendation, movie recommendation, etc. And based on these simple tasks, which are either at the node level or graph level or edge level, we can also do more complex downstream applications such as recommendation, entity resolution, question answering, and graph design. So clearly, graph machine learning is very important considering this kind of wide set of applications in real world. Now, in this space of graph machine learning, we are looking into the interactions and the synergies of graph data management and graph machine learning, how they can benefit each other. The graph data, they actually goes through a series of steps before these machine learning models can be applied and we can get good results in different downstream applications. This starts with graph data construction, graph data cleaning, and also graph data augmentation. Then we need to do the embedding or the representation learning of the graph nodes, of the graph edges, and also the graph itself, followed by the training of the graph neural network model. And then based on that trained model, we perform different kind of downstream tasks such as recommendation, entity resolution, question answering, etc. And last but not least, in this data pipeline, an important aspect is explainability, or in the data management term, we can also call it provenance. So we want to understand which part of the graph data and the model is the reason behind this kind of decisions. Because the deep learning models are black box, and we are using them for different kind of critical applications by the domain experts, such as healthcare, medicine, etc. So they not only need good results, but they also need to understand the decision of the model. And that's why explainability is very important to deploy these kind of deep learning models in the real world. So we are looking into different steps.
Arijit, so in all this discussion, it does not make a difference if you have a collection of many small graphs or if you have one large graph. So all these techniques apply in a similar way.
That's a great question. And the answer on a high level is yes. For example, some of our works that we recently published for graph classifications explainability would also be adapted for nodes explainability. Yes, node classifications explainability. So it is possible, but sometimes you need to make minor changes. For example, what may be important for the entire graph, which would be the some subgraph, it might be different if you consider a single node. It could be only limited within its neighborhood. So some input and some methods might be slightly different, but overall it's yeah, there is a similarity. Okay.
Uh, yes, sorry, Arjit, I just want to ask you a question. How is it really? Can we really do this also the transfer learning here in the context of the graph embedding? Is it applicable to use a model that is trained on a subset of graph or a distribution like Timmy just mentioned on
Yeah, great question. So we are doing some kind of pre-trained models. We are using that, right? So which could have been trained on another set of graphs, and we are trying to see. Probably I will not talk a lot about this one. This is an ongoing work, but we are trying to see how well this works on a new type of data. Is it classifying it well? Is there some problem with the fairness on the new data because of some sensitive attributes that probably you have not considered during pre-training, etc. So yes, all of these things could be considered in this model, right? Transfer learning could definitely be an interesting thing, right? Especially if you are using pre-trained models.
yeah, thank you.
Yeah. Okay, so let's continue. And yeah, so this is the interesting data pipeline. There are different steps, and we are looking into these steps and seeing how graph data management and graph machine learning can benefit each other. So here I listed a few representative works that I will talk about. And for example, in the context of graph embedding, graph data management and systems can help a lot to make them scalable, to also take care of the dynamic updates because these graphs are also updated in a very fast manner. Then in terms of, let's say, explainability, right? So we are also looking into different kind of data management techniques, such as graph views, graph pattern mining, and user-friendly explanations to make these explanations much more usable to domain experts and also configurable. So this is where some applications of graph data management can benefit in graph machine learning. And then on the other direction, we also see the potential of graph machine learning to help in data management, such as different kind of downstream tasks, for example, question answering over knowledge bases and knowledge graphs. So question answering or query processing is bread and butter for data management. And we see that the machine learning models can help in many ways. For example, converting the natural language text to more structured queries, or even deal with incompleteness of these knowledge graphs or approximate matching with respect to user's query versus the structure of the data. So this is the synergy that I will elaborate more, and more in the context of explainability as well as in the context of knowledge graph query answering, so that you can get both the flavors where data management can help in machine learning and also graph machine learning can help in graph data management. But just to give you an overview of some of the areas that we are broadly working. So we are working on graph search or graph querying, including knowledge graph search, and I will talk about it in the second part of the talk. And then we are also looking into uncertain graphs processing, where we can have uncertainty with the edges. And we are looking into some of the fundamental graph problems such as shortest path, reachability, densest subgraphs, and also embedding or representation learning over this kind of uncertain graphs. Then graph pattern mining or complex graphs mining is also very critical to understand hidden relationships or correlations across different entities. And I will show some application of graph pattern mining in our recent work of graph neural networks explainability. And no surprise, we also need to deal with systems because when we want to support this kind of querying and analytics and machine learning, we over large scale data, or lot of graphs, right, then we need to have support from distributed systems. So we recently also have some work on how to make these graph embeddings quite scalable using the distributed framework. And recently we are looking into explainability of graph neural networks, which I will also elaborate a bit in this talk. Okay, so let's start with our work on graph explainability. Now, here we mean that we want to explain the results of high quality but black box deep learning models such as graph neural networks. And this explainability can be in two levels usually. One is the instance level. So where you give one test data, it could be a test node, it could be a test graph, and you want to explain why this test data is getting that kind of decision. And usually you identify some important substructures or subgraphs that is the key reason behind this decision. Or it could also be at the level of the model, right? The GNN model. For example, how the GNN model is working for a specific class. Is there any pattern that is more important for that specific class so that we are getting that kind of decision? And it's very critical because we need to talk to the end users who could be policymakers, who could be biologists, data scientists, social scientists, etc. And the applications are very time sensitive and critical. For example, autonomous driving, healthcare. So to deploy these models in a trustworthy manner in this kind of critical applications, we not only need to give good results of these models, but also the explainability why the model is behaving in a specific way. So given that it's a very critical problem, what are the challenges? Well, the challenges comes from the fact that there is no standard definition of explainability or its requirement. It comes from many different angles, such as trust, causality, transferability, informativeness, how well the domain experts understand the decision and the working procedure of the model. It could be at the high level, or it could be even at the level of individual parameter values, etc. So there is no standard notion. And that's why comparing two explanations, which one is better, is also very difficult and challenging. And there are also other technical challenges. For example, the problem could be with the underlying GNN model itself and not much to do a lot with the explainability. Or it could be also because of the interplay of the graph structure and the feature. Because remember that we are not only dealing with the topology of the graph, but also the features or the additional information that are added with the nodes, with the edges, and with the graph itself. So all these problems boils down to one of the fundamental issue that the end users here are the human beings, right? The domain experts or the data scientists. And we want to explain our results to them. And that's why the subjective issue comes into the picture. So we want to make our explanations as user-friendly, as tunable, as robust as possible so that they can really trust the decision of the models. And that's the key challenge, the subjective aspect that we need to take into consideration. Given these challenges, we are working on this problem, and I will elaborate more about our work on how to make the explanations usable, more user-friendly, more configurable and tunable. And we had a paper in Sigma 2024 about it. And then I will also talk about how to make these explanations more robust against minor changes in the data. And this is again very useful because if your explanation changes due to minor edits, then the domain experts may not believe the decision of the model as well as the explanation that you are giving. So let's start with our work on how to make explanations much more usable. So what are the challenges here? Well, in this figure, we see two classes of chemical compounds. One is mutagen, another is non-mutagen. And then we have a pretend deep learning model or graph neural network, and we get very good results, right, when we classify a new chemical compound. And then there are also several explainability methods, right? Researchers are working on it for some time now. It's not a new topic. And we get this kind of explanations. For example, for mutagens, we get the explanations on the left-hand side. And for non-mutagens, we get these kind of explanations. But now when we give these explanations to the domain experts like biologists or chemists, they don't make a good sense of it because of the following reasons. First, they are very large, right? So as you see, they are almost often of the size of the data itself. And then they are not very discriminative or helpful to understand what are the differences between these two classes. For example, if we look at the pattern level, which is exactly what we are doing at the top, then we can say that, well, this benzene ring, it is present in both the classes. That means it is not very discriminative in terms of the two classes, but it is an useful component to make the decision. If you remove the benzene ring, the GNN model will not work well. So it is needed, but it's not very discriminative. Now, what is discriminative? Well, this pattern P12, which I believe probably NO2, and then P22, which I believe is NH2. So these are the discriminative components or the patterns. And if one of them is present, then together with the benzene ring, then most likely it will be classified into mutagen. And if another one is present together with benzene ring, it will be classified into non-mutagen. So if you give this kind of pattern level explanations, the domain experts can match against their domain knowledge, because they already have this kind of domain knowledge from biological literatures that these chemical substructures are the key reasons. And we can help them to actually match their domain knowledge against the working of the deep learning model and its decision. So with this motivation, right, so these are the key issues that we want to solve here. The first is the existing explanations. They can be often very large. And because of that, it can also be less meaningful. For example, they might have a lot of irrelevant or repeated structures. It's difficult to find the discriminative ones or even the common ones across two different classes. And last but not least, the existing explanations are often at the instance level or at the class level, but they are not configurable. For example, what if the users want a common explanation for both classes in a multi-class classification? So here, just to give you an example, here we are showing on the bottom the social network data from Reddit binary, and we find two communities among many others. One is online discussion, another is question answering. These are two different types of communities. And if you look at how people respond to each other, in online discussion, usually it is more linear type of structure, right? One person posts something, then followed up by another person and so on. Or at most, we can see some tree kind of structure when there is a divergence of the opinion, but it's not like a very complex click kind of structure, not like a complete graph structure that you get in online discussion. Whereas in question answering, we get this kind of click structure where there are many experts, or maybe bipartite structure where there are some experts who are answering many questions, and these questions are posed by a lot of other, let's say, common users. So the structures are very different. And if we give the patterns, the end users can understand that, yes, the model is classifying well. And not only that, we can actually tune it, right? We can say that, well, we are interested in both classes. So what are the common patterns? And here we see something in the middle, and we see that, well, this is not complete click, but also not like linear structure. It is something in the middle. So we can also tune the explainability or the explanation. And that's an additional advantage that we are providing through our method. So our method consists of two tiers of explanation. One is the lower tier, which is very similar to the existing methods. We provide the subgraph. That is the key reason behind the decision of the GNN model. And I will explain in more details what I mean by key reason. But of course, this can be larger. But then on the top of it, we provide a higher tier explanation. And that is why we are mining some patterns from these explanation subgraphs so that the users can understand what are the discriminative ones, what are the common ones, and they can also tune it accordingly, right, based on their need or importance of over different classes. Now, going more into the technical details, so we have a lower tier explanation, which we call as explanation subgraph, and we want it to satisfy two properties. These are called factual and counterfactual property. And what it means is that if I keep the subgraph, then I still get the same decision as in the original graph. And here I formulate the problem as graph classification. So this is called the factual property, right? And on the other hand, we have the counterfactual property, meaning if I delete or update this explanation subgraph and keep rest of the graph same, then I will not get the same decision. It will be a different classification result. So we want our explanation subgraph to satisfy this factual and counterfactual property. And then on top of it, we have a higher tier views in the form of patterns, and we call them as explanation view. And the idea is very straightforward. It is taken from graph views. So we want some pattern that can cover the explanation subgraph. And by coverage, we mean coverage based on the nodes that are present in the explanation subgraph. So many solutions are possible satisfying those criteria. And now we also define some quality of these explanation views. And we have two quality measures. One is the explainability, and this is based on the idea of the message propagation. So message propagation can be modeled as random walk. And based on that, we can also define the influence of one node on the others. And we want those nodes in our explanation subgraph that have very high influence on the remaining nodes. So that's what we model. And then we also want them to be diverse from each other, meaning two nodes in the explanation view should not have same setup or similar setup influence. So we also want some diversity. And by combining them, we define the quality of our explanation view. And then we also have the coverage aspect, which is the user can provide how much uh, explanation or what size of explanation they want from each classes. And that's why they can actually tune it, right? They can give more importance to one class versus the others. So based on this, find the best explanation view. Is there a question?
Yes, Arijit. Can you just, I have just a small question about last slide. For to add this parameter for the diversity, how does it have an impact on structure? Since when you enforce diversity, you for sure, I'm not sure if it's for sure, but you kind of lost also information and change the formal structure in the graph to enforce this diversity. So how does this extra configuration impact your explainability, or if it has an impact, a strong impact on the explainability?
Yeah, good question. So, of course, I mean, I'm not giving a lot of technical details because of the limitation of the time. Um, I'm trying to focus more on the applications, the challenges, and how we are giving our solution at a very high level. But yes, this diversity has an impact, and I can maybe somehow connect it to the, let's say, set cover problem or maybe influence maximization problem, if you are familiar with, let's say, influence maximization. So you want to find a set of nodes that are highly influential to propagate your message, right? And let's say you have a budget of K. Now, you want those nodes that are highly influential, but at the same time, you do not want to pick two nodes that have same set of influence region, because then selecting the first node and then selecting the next node doesn't give you a lot of marginal gain. So this is the idea of the greedy algorithm that we are also using, right? And I think set cover is also have a similar kind of flavor. So yes, once you select the first node, then you want some diversity in terms of the next node selection so that your overall or aggregated influence is maximized. So if you don't include neighborhood diversity, I don't believe I have an experimental result in the paper, but we did something right with our students, and we find that, well, the explanation may not be of the best quality because they are actually having same set of influence region, right, compared to what when we add this diversity aspect.
Yeah, I see. Thank you very much.
But of course, we can take it more offline if we are looking for more technical details, how we formulate it, etc.
Yeah, thank you. Thank you.
Yeah. Okay. Great. Okay, and then based on this formulation of or this yeah, this formulation of the quality of explanation view, we define our problem. So we want to make sure that our explanation subgraphs, they are both factual and counterfactual. This is a hard constraint. Then another hard constraint is they maintain the coverage that the user provides, right? But then satisfying those hard constraints, there could still be many solutions. And we want to find that solution which maximizes the explainability. And in this explainability, as I showed in the previous slide, there are two aspects. One is to improve the or increase the influence, but at the same time, you want to make it diverse in your solution set so that your aggregated influence, right, that itself is maximized. And then we did the complexity analysis of our problem. And we find that the view verification is NP complete because of the subgraph matching, because you want to get your patterns that can cover the expression subgraphs, and that requires subgraph isomorphism, and that's why it's NP complete. But then the expression view generation is also a very hard problem, right? We have the proof in the paper, it's S2P complete. Again, I will not go into the details, but the good thing is, which I also give some hints, the problem or the objective function is monotonic submodular, because of this notion of this marginal gain, right? And we want to create some diversity in terms of the influence, and we show that this follows the monotonic submodular property. So that's why you can apply a greedy algorithm with approximation guarantee. Again, I'm skipping a lot of details, but just to give you the high level idea. So we apply a greedy algorithm to select our nodes in the explanation based on their explainability factor, and that gives an half approximation. Of course, we are also satisfying the hard constraints there. And then not only that, we can give a static algorithm, we can also give an online or streaming algorithm. And the setup is, what if all of your graphs in the graph data set are not known beforehand, but rather they are coming as a stream. And in this case, the greedy algorithm gives 1/4 approximation guarantee. Again, I'm skipping those details. And we can parallelize both the algorithms to make it more scalable over a large number of graphs. So let's look at some experimental results. We also have a demo available. So if you're interested, you can again look at into this YouTube demo video, and we have the demo paper also accepted in Sigma. Okay, so let's look at some experimental results. So fidelity plus and fidelity minus are two metrics that can measure the factual and the counterfactual aspect, right? Fidelity plus, it quantifies the deviation caused by removing the explanation. And you want a high deviation because you want your explanation structure to be really important. So that means high deviation or a high fidelity plus is good. And that's exactly what we get for our method compared to some of the competitors. So AG is the static one and SG is the online one. And we see that our fidelity plus is quite good compared to some of the existing explainability methods. On the other hand, fidelity minus, which measures how close the prediction results of the explanation is if I just keep the explanation. So you do not want a lot of deviation with respect to the original classification result. That means lower fidelity minus is better. And again, we get much lower fidelity minus compared to some of the existing explainability methods. We also measure sparsity, meaning how small the explanation is, and the higher the sparsity, the smaller the explanation is. And compared to the existing method, we are quite sparse. Then we also measure the runtime, right? And again, we are quite faster compared to some of the existing methods. And I believe we don't have the comparison with respect to the runtime with existing methods, but here what I'm showing is on two very large scale data set, we can parallelize well, right? So as you use more number of threads, we can actually decrease the running time, okay? So I will conclude the explainability part with one more or maybe two more slides to just give you the high level idea of the robustness. So as I said, right, we are designing these explainability methods for the domain experts. And if there is minor modification in the graph data, and that significantly changes the results of the classification or the result of the explainability method, then it's not really trustworthy, right? The domain expert may not trust the model. And here is an example, right? So we are classifying a chemical compound, and we delete or disrupt two edges which are feasible because of the bond structures, and we find that the explanation changes drastically. And then that may not be a good thing for the domain experts. So can we give an explanation such that if we perturb outside the explanation up to a certain budget, we still expect the same decision and the same explainability result? That's exactly what we want to ensure in our robustness work. So we want our explainability to be factual and counterfactual as before, but we added this criteria of K robustness, and that means that outside the explanation, we can disturb up to K edges. And that should not change the decision of the model as well as the decision of the explainability method. And it could have also applications not just in biology, but also in cybersecurity. We have demonstrated an application. So here the key idea is we want to understand the vulnerable part of a code or an attack. And here the attack comes through an email called invoice.txt, but it has a malware embedded in it. And in order for the malware to be successful, it needs to access this file called breach.sh. But it also needs to go through a process to get the permission first. So it needs to go through root to IDRSA to CMD and to breach.sh. Or an alternative would be IDRSA to CMD to sudoers to breach.sh. So these are the two possible valid attack paths. But in reality, what the malware does, it first creates a lot of deceptive attacks. For example, through these green files and green processes, if you go through these green files, you will go to breach.sh, but you will not get the permission. So that means these are deceptive attacks. But the malware does this in the beginning, and then what some security expert can do, they can put their security efforts on those green files. But that's useless, right? Because that's not how the malware will actually attack breach.sh. So the security expert can exhaust security resources in that process. So what we want is to identify this shaded region which consists of the important attack paths, and what we want to ensure that even if you change something outside this shaded region, you will still ensure, and if you keep this shaded region intact, you will ensure that, well, nothing changes in terms of the decision, etc. So again, this is how we show that the robustness or robust explanation that we are giving is very useful in multiple domains. Now, I will not give into the technical details, but as I said, we want to ensure these three properties: factual, counterfactual, and robust explanation. We are the first to consider these three properties together, and then we analyze how complex our problem gets, etc. So we show that it's NP-hard, and the verification problem, the generation problem is even harder. But we have a nice solution in the paper, which of course we consider some additional assumption. So we not only consider the global disturbance K, but we also consider a constraint of up to B disturbance within the neighborhood of each node. So combining this local and global disturbance and considering some specific GNN model called APPNP, we show some nice theoretical results that the solution can be done in polynomial time. And then again, we also did some parallelization. So I guess I'm not going to the details of the experimental results due to the limitation of time. How much time I can take, Themis?
So we can have another 10 minutes or so.
Okay, good. So then in the next 10 minutes, I will give first the conclusion of the explainability part, and then I will give very high level details of the other direction, which is knowledge graph querying and how machine learning can help in data management. Well, so on the explainability part, right, so I discussed how the explanations can be made user-friendly, interactive, configurable, and robust. And we show the synergy between graph data management and graph machine learning there, in particular, how graph data management, such as graph views, graph patterns, usability, these concepts can help in the GNN explanation. In terms of the future work, we are having some ongoing work here. For example, adding human in the loop, getting feedback from the user, to also incorporate some domain knowledge directly in the explainability aspects, also to provide more human level evaluations to add trustworthiness and fairness, etc. Okay, so that concludes the explainability part, and in the next few minutes, I will give a very high level overview of our work in querying knowledge graphs, and in particular, how graph machine learning can help in graph data management. So knowledge graphs are very popular also these days. It started way back around 2012. It became way back around 2000. It became popular way back around 2012 when Google coined this term, Google Knowledge Graph. And then in Panama Paper investigation around 2016, researchers used graph-based technologies to identify important hidden connections across different rich people and rich countries. It became more popular then. And then in this plot, I show that in 2020, based on Gartner's hype cycle, they put knowledge graph among one of the top concepts. So clearly it shows that it's still very popular these days. And what are the challenges here in terms of querying knowledge graphs? Well, we are data management people. We work mostly with relational data, right? And in relational data, we know that they have very standard schema. So we can use this schema to write our queries. We can do query optimization well. There are already a lot of techniques, etc. But now on the other hand, when you deal with knowledge graphs, they have some structure, but they are more semi-structured in nature. So that means same type of entities can be connected in multiple different ways. And oftentimes there is no standard schema, or even if there is a schema, the schema can be quite large, often in the scale of the data itself. So if I ask the user to understand such a large schema and then write a query in SQL or SPARQL, that's not very user-friendly. So again, the challenges here are coming from the usability aspect. The database users are not the designers of the database. And this has been mentioned as a term called unable to query in a very famous well-cited CMOT paper by Jagdish et al. So we are looking into this problem, that how the querying of knowledge graphs can be made much more usable, user-friendly, and we are taking help of machine learning techniques to do that. So just to illustrate the problem, right? So let's assume that we have a small Wikipedia knowledge graph of different cars, their manufacturers, companies, countries, etc. And over this car knowledge graph database, we are interested in the following query that find all German cars or all cars that are produced in Germany. And there are many ways to answer this query. One way is to do graph matching, which is you can represent your query as a graph and your data is also in the form of a graph, and then you do some kind of subgraph matching such as subgraph isomorphism or some relaxed notion of graph matching. But one problem is, let's say we consider the product age as per the query and there is no product age, but if the user is smart, well, he or she can look into the data and find that, well, there is an assembly age which is synonymous, so you can replace product with assembly, but in that way you can find only one relevant car from this data, which is BMW 320. But there are also other German cars such as Audi TT, such as Porsche 911, right? They're also German cars, but the connection of them with the country Germany in the data is slightly different, right? They're connected by the assembly age to the company, and then the company is connected to the country Germany based on the country. So the key point is, although the semantic meaning of those parts are same as the query age, but it's very difficult and challenging to figure out that, right? And provide more relevant answers, right? So we want to provide more relevant answers by taking help of machine learning, and I'll not go into the details. We are having a series of works on these domains, but just to give you the very high level idea, we are taking help of knowledge graph embedding, and the embedding converts the relations, the nodes in the form of vector. And they can preserve the semantic relationships very well. That means if two things are semantically similar, then most likely they have very similar representation in the vector space. So we are taking help of that semantic similarity to define our query over the vector space. And we are giving more relevant solutions that otherwise you won't be able to find using a more stricter notion of similarity. I'll not go into the technical details at all due to limitation of time, but I'll just give a high-level overview of another work here, right, in the context of querying. So we are not only answering factoid queries such as find all cars produced in Germany, but we are also turning it into aggregate query in another paper, right, where we are interested in aggregation aspects such as how many cars are produced in Germany or what are the average horsepowers, right, of those cars produced in Germany. So here what you can do is, well, you can first find all the solutions that are relevant and then you can apply the aggregate operator. But what we realize that that's often not necessary because that could be very expensive. What you need is some relevant answers, maybe some samples which are more relevant with respect to the query, and then you can define your estimate on top of those samples together with some error bound. So all we do is we do some random walk, right, which are more biased based on the relevance of the query. So we can define some weight based on the relevance with respect to the query, and we can bias our random walk so that we can get more relevant samples. And based on those relevant samples, we can define our aggregate operators. And we can also give some error bounds based on central limit theorems, etc. If the users are happy with the bound, then we can stop. We don't need to sample more. But if they are not happy, then we can do more sampling and we can improve these bounds in a more iterative way. So this also adds some kind of user friendliness, right? You can stop early instead of generating complete set of results and then doing the aggregate on top of it. So that's all the technical things I wanted to say. And let me conclude now due to the interest of time. So in terms of the graph query, right, the graphs that we deal with so far are let's say, a bit simpler, right? So we have the nodes, the ages, and some of the labels, but these labels can also be more complex. For example, you can have a table in the form of a label, such as Wikipedia tables, or you can have images, you can have some Wikipedia text, etc. So that basically goes to the direction of multimodal knowledge graph querying. And we believe that our vector-based query processing can be a holistic mechanism there because all these types of data, such as text, images, graphs, tables, it can be represented in the form of vectors. And now we can have a holistic vector representation, and hopefully some of our querying techniques over these vector databases could also be useful when we deal with multimodal knowledge graphs. So this is an ongoing and future works or the directions that we are looking into. And in that context, language models and vector databases could also be useful. Language model could be useful if you have a lot of text or table kind of data. Vector databases will be useful to manage those vector data. So the big picture of our research is, yes, we are working in the space of big data, big graphs. It's very much data driven. But two other aspects because of which I like this research domain is, first, it is interdisciplinary. We require domain knowledge and expertise from many different areas such as machine learning, databases, graph algorithms, stream algorithms, etc. And last but not least, this is also very much application oriented. So we have demonstrated applications of our research in web search, in business analytics, in healthcare, etc. So the main takeaway, well, I started with the synergy of graph data management and graph machine learning in the entire graph data pipeline. And we are working on different phases of this pipeline, and we are trying to see how data management and machine learning can benefit from each other. I have discussed the explainability aspect where the data management techniques such as usability, views, patterns can help in machine learning. And then on a very high level, I went through how machine learning techniques can help in data management such as query answering. So the future direction, well, LLM is the new kid. Everyone is talking about it. It's the new deep learning technology, and there are many ways how you can incorporate the synergy of data management and machine learning here. So we are particularly looking into the retrieval augmented generation of the LLM, where you can input a lot of relevant knowledge from, let's say, knowledge graphs to improve LLM's accuracy and consistency. And we are looking into some downstream applications here, which LLM is most popular for, such as fact-checking, code explanation generation, schema matching, etc. So with that, I will end. And once again, thank you. And I'll be happy to take questions.
Thank you very much, Arijit. So that was very interesting. Are there any questions? I guess I can start with a question. So Arijit, I was wondering, have you been applying any of these techniques on some real graphs? So I was wondering, what are the maybe problems when you try to do this in practice? Are there any special constraints or more requirements that come up? And on the other hand, what are the insights that you're getting by applying these techniques on some real data?
Yeah, great question. So there are many challenges. One of them is, of course, security and privacy. We are working with the biologists and the hospital, the doctors, etc., right? And they don't easily share their data. And even if they share, it's very anonymous, and like maybe we are missing a lot of relevant information. So ensuring security, privacy is a big thing. And sometimes you also need to do in a federated learning kind of way, so that you are still learning your model across multiple slices of the data, but maybe there is no common data platform. So that's a big challenge. I don't think we have a solution for it now, but these are some of the issues that we are seeing. Another thing that recently researchers or the domain experts are interested is about fairness. What if the model is making some discriminative decisions against some groups or populations, right? How can you ensure that? So that's also something that the social scientists that we are working with are also very interested. And again, we don't have a solution, but we are at least trying to see if we can understand from the explanations, we can provide an understanding that, well, the explanation is making because of the explanation, we can say that the model is making the decision mostly because of the sensitive attributes. So that's something that we are also looking into.
So a follow-up question. Can you say something more about the fairness that you just mentioned? So this will be very interesting for us. So is fairness a problem that is orthogonal to what you described, or is it something that should be addressed in combination the other analysis tasks that you're running?
I think it is very much part of the whole picture, right? The whole picture, if you say in terms of some keywords which are popular these days, such as responsible AI, right? So, or explainable AI, right? So there, fairness is an important aspect, right? Where that the machine learning model, right, which is kind of black box, is actually making the decision uh, based on some sensitive attributes or based on some irrelevant things that probably it should not make the decision on. Uh, for example, these LLMs, right, these days, these are all pre-trained models, and we have often haven't seen what data they have considered for the training, and on the new data, even on the new downstream task, how the model is generalizing. So definitely, at least giving some insight in terms of the fairness would be the first step. And then if we understand that, well, the model is making the decision in an unfair or not so logical or relevant way, then how to resolve it could be the next step. Right now, what we are in the very first step, right? So we are trying to identify if some unfair things is going on in terms of the decision making. And we think the explainability can help. It's still an ongoing work, so I don't have a result or anything concrete to talk about, right? But the direction we are taking is to find out some counterfactual evidences. For example, if two items are very similar in terms of their features, structures, neighborhood, etc., but they are getting different decisions, then can our explainability help to understand why these two items are getting different decisions? And perhaps from that explanations, we can also figure out that, well, um, the model is making decision not based on something relevant, but maybe based on something which is relevant for these downstream tasks. That's the very high level idea.
Yeah.
But yeah, there is a long way to go to make it more concrete.
Okay. Are there any questions from other people?
Yes, Amy.
Yeah. Yeah.
Hello, thank you, Arijit, again for the rich presentation. So I have just one question about the explainability you started with begin actually. Um, it's about the part where you subtract or extract the most important subgraph to do the
Yeah,
decision
I
actually.
will go there.
What what are the techniques used actually in the domain of graph neural network to identify those important subgraph or edges, like scoring strategies, or more heuristic that you use in kind of brute force manner?
Yeah, good question. So I have discussed two words here. One is on the user-friendly and configurable explanations based on the top-level patterns and the bottom-level explanation subgraphs. And the second work was more on the robustness side. Okay. So there are theoretical aspects to this work. It's not completely heuristics, right? I mean, due to the limitation of time, I'm not going to the details. So for example, on the first work, right, we give 1/4 like half approximation and 1/4 approximation, and these are theoretical results. And basic idea is you have the greedy algorithm, right? And then you also need to maintain some kind of fairness constraint. And of course, don't confuse this fairness against the discussion we had, the other fairness. But the idea of the fairness here is the coverage that the user provides, right? So user also wants to cover a certain number of nodes from each classes. So we want to satisfy that requirement. At the same time, we want to maximize the explainability in terms of the inference maximization. So we develop some algorithm. It's not a new algorithm, but it's this kind of greedy algorithm with half approximation or 1/4 approximation, but can be used here to solve this problem. So this is the theoretical thing that we are applying here to solve our problem in this domain on this specific one. The second one, right, is about robustness. Again, I did not go at all into the technical discussions, but I showed these complexity results, right? So the verification is NP hard, and I can give you an idea. So what this KRCW does, it says that outside the explanation, right, I can change up to K edges. And that should not change the decision of the model as well as the explanation. So now the verification, right? Given an explanation, is it KRCW? You can imagine that, well, you need to try all combinations outside size K, and then you need to check one by one, right? If it is still satisfying these factual and counterfactual aspects, right? So that's why there are so many combinations, and that's why it's NP-hard. Of course, there is a formal proof, right? I'm just giving you the high-level intuition why it becomes NP-hard. And that's why the generation is even more challenging, right? It's co-NP-hard. However, we also have a nice theoretical framework there, and this is when we add additional constraint, right? So one constraint we add is this B, the local budget, and this is coming from a theoretical work in the machine learning domain called certifiable robustness. Okay, so we take ideas from that domain, and when we add this local budget constraint, which is how much the degree of each node you can disturb, right? So we also add this constraint, and we consider a very specific type of graph neural network called APPNP, which is slightly different than what exactly I presented earlier, the graph convolutional neural network. So combining these kind of constraints, we still give a polynomial time algorithm. So yes, if you're interested, there is some theoretical angle to there as well, which unfortunately I could not cover. And yeah, I mean, I'll be happy to talk more, maybe offline.
Yeah, for sure, for sure. Thank you very much.
Are there any
Very relevant and interesting questions. Thanks.
Are there any other questions? So let me ask one last question. So you also mentioned the aspect of execution time. So I was wondering, all these techniques that you talked about today, what do they entail in practice in terms of computational time? So is all that things that we can do efficiently, even in real time, or are there scalability challenges that we need to work on?
There are scalability challenges, and you actually pointed to a very important and interesting direction. So most of these works, right, like explainability or even embedding, etc., right? So they are started mostly by the machine learning people, right? And if you look at the papers, of course, there are several exceptions, right? But many of the machine learning papers, right, they do not care much about the efficiency, the scalability, parallelization, etc. But we, the data management people, we can contribute a lot there. And when we actually tried many of the baselines, we find some of them are not very scalable, right? So some of them may even take days and so on. So since we are targeting the data management venue, which is the main immediate reason why we are looking into this efficiency and scalability. So yes, in our papers, we are providing the efficient and scalable solution using parallelizations, etc. Whether they meet the need of the real domain at the real time, we don't know, but there are definitely scopes of improvement. For example, I gave this streaming algorithm or the online algorithm. So probably it matches the requirement of the streaming, but we haven't tested in a real setting, right, with real users and getting their feedback that are they happy with our results? We don't know. We only show that yes, it can be parallelized and yeah, we improve our running times compared to the baselines. But that's a very interesting direction that we, the database people, can also look into.
Yeah, well, I was going to say it's not only a challenge interesting to data management researchers, but it's also a challenge when we try to apply all these techniques in practice. So it's relevant to everyone at the end.
Yes, yes, yes. Yeah. Agree.
Okay, so let's so thank you once again very much for this very interesting talk and the discussion. It was very nice having you with us today.
Thanks, Temis, and thanks everyone. It's very
Yeah.
nice. Bye.
And thanks everyone else for participating. Okay.
Thank you very much.
Bye everyone.